2.6, completing function model validation. Here we go.
Throughout this course, we will have many opportunities to work with and create models based on a given data set. Three particularly important examples of this are linear, quadratic, and exponential models. Because these three types of models occur frequently in the real world, there is a heightened focus on them in AP calculus. On the AP exam, students will be expected to determine which model is most appropriate.
Most.
Given the set data, there are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential model is
Most.
given data set.
All right. I personally don't like the word most appropriate because it's not concrete like most of our mathematics. It's more wishy-washy stuff. All right, and so this doesn't have any relevance too much to calculus. However, it's more used in the stat world. All right, but anyway, here we go. So let's look at some different types of models that we can have. And so this is a linear model. It is not a linear function. It is a model. And the reason between why it's different is that it's a model because does it actually go through all of these points? No. All right, so it's not the graph of the function, it is the model like that it's going to kind of make. It's that best fit type of thing. And so a linear model still has a constant rate of change. So my algebra slope is similar, all right, to each other. It's so it looks like a linear even though it's not because it's a model. All right, quadratic, it's going to make that U shape type of thing. All right, it could be like the N shape, but it's a U reversed. But anyway, so the rates of change are increasing and then decreasing at a relatively constant rate. So the rate of the rate is the same. All right, and so anyway, that's what makes that shape. And then an exponential is proportional. Okay, are they exactly proportional? No, it's a model again. And so on this one, my b would be greater than 1. And so what makes it go this way? When b is between what? 0 and 1, exactly. All right. And so those repeated outputs are being multiplied. All right, so that's what makes it roughly proportional. All right, let's play. So on these examples, you have to figure out what is most appropriate, linear, quadratic, or exponential on these. So we have a set of data, and so now we're just going to like graph them. So 0, 11, we're going to graph 0, 11, and then 2, 8.2, so it's about there, and then 4, 5, so we're right there, and then 6 at 2.3, we're right there, and then 8, negative 1, so now we're down there. And if I were to try to connect these dots, they're not going to connect perfectly. However, what does it look like it might be? It might be linear. All right, and so this is a linear model. It is not a linear function. It is a linear model. Make sense? Cool. All right, so let's look at part B now. So we're going to plot these as well. And so if we have a negative 1, 2, we'll plot negative 1, 2, and then 1.5 and 5.5, 4 and 10.5, and then 6.5 and 5.75. 9 and 2.5. And so on this one, what might it be? Is it linear, quadratic, or exponential? Or it's gonna look like quadratic. Now, you're not going to connect the dots perfectly on this one. However, it kind of go like something like that. All right. It goes from increasing to decreasing. It has symmetry around x equals 4. Okay. Again, we don't know exactly what that will be. However, we could do a regression with it. All right, so let's look at C now. So let's start plotting. So we got 1, 10, 3, 5.2, 5, 2.4, 7, 1.3, so forth. All right, and so what might this one be? This might be exponential. Now, is this a growth or is it decay?
Decay.
It's a decay. And what does that mean if it's a decay? Our b is between what? 0 and 1, exactly. All right, so this is an exponential model, and so there we go. All right, let's look at D now. So we're going to plot these. So we have negative 2, 2, and then 1, 3, and then 4, 4.5, and 7, 6.75, and then 10, 10.25. All right, and so what might this one be? This one's also exponential. All right, and what kind is this one now? This one's a growth. All right, and so this is an exponential, and this is more of a growth. Wow, I totally misspelled the other one. Exponential. All right, there we go. All right.
When we create a model, we can use our model to predict values for the dependent variable output given an independent variable input. When using a model, it's important to remember this is only the predicted value. If we use the input value from the known data point between the predicted output using our model, the difference between actual output and our predicted output is called a residual.
All right, and so the residual is the actual minus the predicted. So we did this in Unit 1 as well, and so a residual is actual minus predicted. Is it predicted minus actual? No, and so that's what you guys messed up on the test sometimes. You guys flipped them. It is always what? Actual minus predicted. All right, let's play. So we have this example.
The weight of newborn babies
Oh.
can be modeled by a linear function in the first 4 months after birth. Selected values for the weight WT in kilograms of a particular newborn baby are given in the table above, where T represents the number of months since birth. Use the regression capabilities used to calculate and find a linear model of the form y equals a plus bx for the weight in kilograms of this particular baby x months after birth.
All right, wonderful. So we're going to make a regression, and so now we're going to go to what? Stat and then edit. So once we have that, we're going to go to stat and then calc, and then we're going to go to linear regression number 8. All right, we're going to go to number 8, and so then we're pressing enter, and so we're going to store that. And how do we get to store again? We go to alpha trace and then set it as y1, and so then when we calculate, we now have that right there. All right, and so now we have our a and our b like that. Okay. And so now we end up having y equals 3.34 plus 0.8 times x. All right. All right. And so now part B. Kyler.
Use the model found in part A to predict the weight in kilograms of this baby 2.5 months after birth.
All right. And so now what are we going to do? We're going to substitute in 2.5. And so now we're going to find y of 2.5. All right. And so then on our calculator, we can just do what? Alpha trace and then parentheses 2.5. And so on that one, we get 5.34 kilograms after 2.5 months. All right, keep going.
The actual weight of this baby 2.5 months after birth was 5.5 kilograms. What is the residual for this weight? Did our model underestimate or overestimate the weight of this baby 2.5 months after birth?
All right, fantastic. How do we find a residual? The actual minus predicted. So what was the actual? 5.5. And then we're going to subtract our predicted value, which is used with our regression model. And so we subtract out what? 5.34. And so we end up having a residual of 0.16. All right. And so what do we know about our residual? So did our model overestimate or underestimate? This was a what? An underestimate. All right. It's an underestimate of our actual. All right. All right. Kyler, pick a reader.
Continue residual plot to check the appropriateness of a model. A residual plot shows all the residuals for a set of data and can be used to determine if a model is appropriate for a given set of data. If a model for a given set of data is appropriate, a residual plot should appear without a pattern. If we can see a clear pattern in a residual plot, then the model used for the regression was not appropriate.
All right, I want you to star, I want you to circle, I want you to do something to that bolded middle line. All right, and so they use this in AP Stats. However, they actually only use 3 different models in AP Stats for these residual datas. But in pre-calc, I guess they are going to give you even more than that. But anyway, this is really what I want you to see. So if we have a residual plot, and if it does not have a pattern, that's good. All right. Then what our data set was appropriate. All right. It was most appropriate. If it does have a pattern, it's bad. All right. And so anyway, that's really what I want you to know. All right. So if our residual plot has a pattern, bad. If it does not have a pattern, that means it's good. All right. All right, so let's look at these now. So if you look at example 3 with me, all right, so this is an exponential regression used to model, and then this residual plot was given. All right, and so what do we notice about the graph? There's no pattern. And so what do we know about the exponential model? Is it appropriate or not appropriate? It's appropriate. Because why?
This shows no pattern.
There shows no pattern. All right. And so which one says that?
C.
C says that. All right. And so really that's how our course is going to be modeled basically. You're basically looking to see if your residual plot has no pattern. That's really what it's going to be about. All right. Pretty good? Cool. All right. So let's keep looking at example 4 now. All right. Mary, pick a reader.
A group of AP pre-calculus students used a set of data to create a linear, quadratic, and exponential regression model. After creating the 3 models, the students created a residual plot for each model type, see above. Based on the 3 residual plots above, which model was most appropriate for the data? Give a reason for your answer based on the residual plots above.
All right. So linear regression. Did it have a pattern? This one had a pattern. Sure did. All right. Does quadratic regression model have a pattern? Yeah. How about the exponential regression model? Did that one have a pattern? No. And so which one is most appropriate on this one? The exponential. All right. And so this was the most appropriate model because why? The residual plot had no pattern. All right.
Example 5. Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the side of several downtown buildings. His mural will consist of many painted circles of various sizes where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r in feet.
All right. Fantastic. Keep going.
Should Mr. Passwater use a linear, quadratic, or exponential model in this situation? Explain your reason.
All right, so we're actually going to all the way back into our first chapter, our first unit, the very first lesson. All right, and so would linear, quadratic, or exponential model better in this situation? What is a mural painted on? Canvas or a wall, probably a wall if it's outside because it's a building. And so what kind of dimensions does a wall have? Is it linear? Is it area? It's area, isn't it? I'm going to paint on a certain area. In what kind of feet or meters or whatever unit you're going to use? I'm going to use squared feet. Does everybody make sense? Because that's how area is measured. And so if I'm going to use squared feet, what model would model it best? A quadratic. All right, because that's squared. All right. Do you remember doing volume? Volume would be modeled by a what kind of function? A cubic. All right, same kind of thing here. And so this would be what? Quadratic, because why? Because of squared feet. The area is squared feet. Or squared units of some kind, all right? Doesn't have to be squared feet. Maybe you're in Europe and you're using metric. All right, part B.
After creating his model, Mr. Passwater uses it to purchase different special paint colors to use on his mural. In this situation, do you think it is more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Give a reason for your answer.
All right, what would be better, an overestimate or an underestimate? An overestimate. All right, you want an overestimate. Why? So he has enough paint. Exactly. All right, so you don't want to run out of paint. All right.